I do want to get a photo of that.
Let's see, when I get started, I guess, no, I'm here. So the homework, let's see, so everyone kind of got this, this business, so the TG, it's a rubber. That's why it bounces back, the rubber ball. That, like, if you, like the height you drop it from, so there's almost like no loss, right? So that the loss drops down. When you get near TG, so I did find this guy. So this is a rubber that's at TG. Oh, no, that one's not the rubber. Oh, no, here it is, but rubber at TG. Just like stops, right? And then when you get below, it's glass. So all you have are these bottles when I'm going to throw it. It'll bounce again, right? So you have, when you're at TG, so if you think about the amount that it doesn't recover is like almost the whole thing. So that's a peak. And when you're at the upper end, it's like almost nothing. It drops down. When it's a glass, it bounces again. So one's a entropic elastic. So it's like a jump rope. So the temperature goes up and it pulls it in. So basically it's springing back because of the wanting to kind of the jump rope when it's swinging. Or if you have a gas piston and the gas atoms are moving around, and it's like it's springy when you push it. So it's totally elastic, meaning that you recover all the force that you put into it. And so then the glassy one's elastic because of enthalpy. So one's entropic, the rubber, and the other one's enthalpic. So when you actually deform a solid, the bonds actually squish. Right. So it's like it wants to go back to the normal bond length. It's actually changing the bond length in glass. Right. And then in the rubber, you're just changing the end-to-end distance of the chains. So anyway, that's that business. And anyway, all right, so I'll try to get some liquid nitrogen from chemistry, because you can take like that ball, you can go through that whole transition from a glass to this. You can kind of see it happen, but anyway, you need some liquid nitrogen to do that. Anyway, hopefully do that. So anyway, that's that thing. I think like half the people kind of got that. Anyway, I didn't really talk about and you can go through the Dubai relaxation business. So it's got, like, when it's right there, so the frequency of it hitting the table matches perfectly the frequency of the vibration of the molecules. So it absorbs all the energy of the dropping. That frequency changes with temperature. So you get this, basically the peak occurs because you're matching the frequency at that temperature. And it's going to follow the Arrhenius dependence, like an exponential energy over KT gives you the frequency. So basically it'll change exponentially with the temperature. So that's one part of this. Temperatures, these are kind of relevant questions, even though they seem odd, but and then this DSC I never talked about. So I forgot, I didn't remember to put it in. So I actually afterwards I stuffed in some things about TG in here. There's this thing from Southern Mississippi. So there's like 4 Polymer Science schools in the country. There's like Case has one, Akron, 2 of them are in Ohio, and UMass Amherst, UMass Lowell. There's 5 in Southern Mississippi's, like the 5th one, I guess. So Southern Mississippi made this macro Galleria thing. It's supposed to be general interest thing for, it shows you what a DSC is. It's kind of like low scale to figure out what all the things are in polymers and plastics. In fact, so if you go back to the, this has been around a while, so I'm surprised it's still up actually, but someplace you can get to their parent page here. Glass transition, polymer glass transition. Some of this will link to the whole macro Galleria. I see that right here. So anyway, it's got like, I guess level 1 is like complete idiot and level 6 is something higher than that. It's kind of worth fishing around it. It's got a lot of things in it, but the thing on glass transition is pretty good on the DSC. And then this thing is from my webpage. I used to teach a class called characterization, so it's got stuff about the DSC in it, but kind of what a DSC curve would look like. So basically you have, so you're putting in a heat rate, so like watts are going into it. So basically you have a filament that's heating. You're putting in energy into it, so it's watts. So it's like joules per second, right? So that's a rate, but you're heating it at a constant rate, like degrees C per second. So if you divide, and that's a fixed number. So if you divide the joules per second by the heating rate, you get dq dt, which is the heat capacity. So if the units of this are watts, it's not heat capacity. If you divide by the constant heating rate, you get heat capacity. So basically this is a plot of heat capacity versus temperature for where you're doing a temperature scan. So the heat capacity of the liquid's higher than the glass, so you have a jump in it. And this, all right, this axis can be endothermic or exothermic. So you can, the numbers will flip. It'll be like negative numbers, depending on if you define it. So you have to point like which direction is endothermic on this side. And if you say endothermic, then the heat capacity of the glass is lower, liquid is higher because there's more motion in a liquid. So it can store energy, translational energy, the molecules. So it should just be a step function, like boom, boom, right? And then you see this overshoot because it's heating at a finite heating rate. So that's like the lag, basically. If you heat it faster, you get a bigger overshoot here. You could think of it as that. So usually if you have a peak in this, or a dip or a peak, it's going to be, in other words, if you integrate that peak, you'll get the enthalpy of melting for the material, like how much heat it took to melt it. If it's a metal or a ceramic, it'll just be a spike here. But for polymers, because there's different melting points, because the crystal thicknesses vary, then you get this broader pump on it, right? And also, so once you get below TG, everything's locked in. So everything's got a finite heating and cooling rate. So if you take like a water bottle as PET, it'll crystallize. But because it's extruded and it cools too fast, you quench below glass transition, which is something like 130 C, and then basically it's a glass, it can't crystallize. Except for at the point, like if you look at the bottom of the water bottle, there's a nib where it was injected. So you make a bubble, make a tube, you nip it at the bottom and you blow air into it and it fills out the mold. It makes a water bottle. It all happens pretty fast. And then the machine spits that thing out. It's called blow molding, right? So anyway, if you look at the bottom, at the nib, it cooled slower and that's all white because it's partially crystalline. Right? So it can that whole water bottle can crystallize if you get it up above TG, so above 130. And then it's going to start to crystallize. The crystallization rate is fastest kind of halfway between TG and the melting point. So in other words, the molecules move around faster as you heat it up, so they can get into their conformation for crystallizing. But the driving force, the enthalpy of crystallization, is highest the deeper the quench, where things stop moving. So you have a competition between the motion of the atoms and the enthalpy driving them to crystallize. So basically the enthalpy is biggest over here, motion is biggest over here. Somewhere in between, there's a maximum crystallization of the polymer. So you'll see a dip in this, it's absorbing energy, crystallize, or it's releasing energy to crystallize, it's absorbing energy to melt. So that's called cold crystallization. So you have your water bottle, heat it up, you see a glass transition. So there's a step change in the heat capacity. Then at some point you reach the maximum rate of crystallization. There's a dip where it's releasing energy to crystallize. And then you get to the melting point and it zooms up, and then you get an enthalpy of melting in it. And then you just have a liquid after that, where it's just a constant heat capacity. So that's kind of the picture of a polymer and the DSC. The machine itself, there's a picture of the machine here too. I guess the wiki DSC as a picture of it. It kind of looks like that. You have two pans. There's a comparison pan and the sample pan. You put your stuff in a little sealed platinum or aluminum tray, depending on what you're doing, what kind of material you're using. There's a temperature range you're using. So for polymers, it's usually an aluminum tray that you put in there. Little like tray with a lid on it. A little bubble. You don't want the bubbling to get into this heating element. And then it monitors you can have two ways to do it. You can heat up the whole thing and monitor the temperature in the two, and there'll be a temperature differential. Or you can monitor the temperature in the two and keep the heating and monitor how much heating you do. So if you monitor the heating, that's a DSC. If you just monitor the temperatures, that's a DTA, differential thermal analysis. They kind of end up with the same curve. One's easier to make. Like a DSC's got a servo computer thing in it, so it's harder to make. So the wiki kind of shows some of that. This is kind of that generic thing, cold crystallization and melting in the glass transition. I don't know, there's a lot. Actually, when you Google DSC, like you don't find this stuff. So the links are kind of useful here. And the companies that make it, like Thermal Analysis, a couple other companies, and that they used to have good web pages on this, but I couldn't find one that was decent. Anyway, so that like this paper is kind of all about DSC. So I thought, I should have put that in. I mean, partly about DSC. And there's a question about it, but I didn't exactly talk about it in class. So it's there now. Some like two groups answered that really well, and then everyone else kind of didn't know what a DSC was. So that's what a DSC is. If you want to see one, they're down like the characterization lab in the third floor of the Manti Center. You can go in and ask Mel's down there, Melanie, and she can show you the DSC. Want to see it? And also there's one in the chemistry. The chemistry chemistry has a characterization center. It's on like it's like one floor below wherever you walk into chemistry. I don't know what floor that is. Basically, you can go in and look at one there too. Like it's Nakati Kaval. Did you guys take the chemistry intro lab or something?
Yeah.
Did you have him? Or yeah, he's a really good guy. So he'll tell you you're off about DSC. Actually, we should just do a tour of his stuff in there. And he's got like IR, ramen. He's got some other things. Oh yeah, nice. I mean, the water company will do that for you too. But
I went on the Cincinnati Waterworks and like we had lead pipes leading into our house.
Uh-huh.
Obviously, they might have updated it, obviously.
Yeah.
Jill Webster in the lab worked for like a water treatment company. So she explained to me that, we work with lead pipes now and they build a biofilm. So like, if it's not.
That's comforting.
Yeah,
But they're like, because we do tours of the waterworks sometimes. Actually, we did it last semester. And they have a whole lab where you can just give them a sample and they'll give you the results on it.
well, I paid for tuition here. So.
Yeah. Nakati's a good guy. Yeah, he'll help out.
Yeah, he's super awesome.
Yeah, he's really helpful. But anyway, so yeah, he's got a DSC down there. So I mean, some of his stuff is like higher temperature. He might have a DTA. So like if you're doing metals, a DTA is better because you can't get to such a high temperature. Like you can't get to a 1500 C with a DSC. So, also if you want to, like say you want to do DSC in space or something like that, which people have done, then basically you do a DTA because it's much easier. You just have a block heater with two thermocouples and that's it, right? But this thing, you need like a computer that servos the thing and controls the heat flow to match the temperatures on it, which is slightly more complicated. But anyway, a lot of times you'll see DTA when things get exotic, like they want to do put a DSC into a cryostat. Like a cryostat is going to go to almost 0 Kelvin, like maybe 2 Kelvin. So they put a DTA into it, not a DSC. It's easier to do that. Anyway, so there's a lot about that, but basically there's kind of a need to know approach in this thing. So hopefully you can kind of figure it out. this thing I talked about, I think some people got this, some didn't. See, then I should have said Fox equation, not Flory-Fox. That's my mistake, but. So the Fox equation is a thing that he uses in the paper, not the Flory-Fox. So, but I think most people kind of got that thing. And then everyone got E, I think. So that's about it. The main thing is the DSC. I didn't talk about it before. So any questions on that thing? No, okay. Right. So let's see. That's the old stuff. All right, so I went through. Yeah, it's really hot in here, huh? Sometimes there's a thermostat. Oh yeah, back there. Hold on a second. Sometimes it actually works.
Yeah, I had a folder on my school Google, Google Drive, all of them. So that's all the ones I could find. I have a few of them. There we go. Nice way down.
Or is that still is? You could open the windows and actually go back. Anyway, so yeah, so I went through Van der Waals last time. You can look at it if you want. So I went through up to the second order term. You can also go to the third order. So if you say this is binary interactions, so you square the concentration, then you can just add in another ternary interaction. So you can put like a third order into the Van der Waals, and in that case, you take the viral and expand it to the third term. So you have like the first viral expansion, whatever that is, here, B2 and B3. Then you'd say like what's B2 and what's B3 in terms of those parameters. If you don't include the C, then this is just the excluded volume squared. If you include a ternary interaction in Van der Waals, then you get like this equation. So you have like the square of the interaction. Just B3 is going to have squared volume units. You have square of the hardcore and some kind of a ternary interaction, which would be kind of a weird thing, hard to imagine. You have like two things you can say, like they repel or attract. Then you put in a third thing, and it's kind of like how the third thing interferes with the first two. It becomes esoteric. It's hard to figure out exactly how that works, but so the third one approaches the first two, and it can interfere with the interactions of the first two. And that's kind of ends up giving you this B3 term. So this people usually just stick with B2 because it gets too hard to figure out what B3 is. But we'll look at later on, we look at coil collapse, we'll look at B3, and then we'll have like a B, we'll have actually he uses a capital B and a capital C for those, the guy that will be following Grossberg. So anyway, so you can do like a ternary, binary and ternary interactions on it. And you could keep going if you wanted, like you could extend that, but anyway, and then we by comparison of the Boltzmann and the Gaussian function, you can get an energy for the chain. If you want, you can include an excluded volume term, which is just the volume for one exclusion is the volume divided by the chain volume cubed. And that it doesn't exclude is 1 minus that. And then how many times that could happen in the chain is n squared over 2. So if you do that, take the log of it, take the exponential, you end up with this expression, which is of the same form as that one. So you can just add in that term here. And then you're accounting for a self-avoiding walk, which ends up giving you this, instead of n to the 1/2 or a fractal dimension of 2, you end up with 3/5 or a fractal dimension of like 1.67, which is a lower dimension, meaning that it's a larger object. It's like if you have a dimension of 1, that's as big as you can get. That'll be a rod. So rod picture spinning around in space. And then if you go down to 2, it's more of a compact object. It's got the drunken walk in it. So anyway, that's what this is. So what we did before was you can calculate the integral of r squared times that Gaussian probability, then you can get the mean squared distance, which ends up being NL squared. In this case, we don't have that simple Gaussian. We have like the Gaussian in this other term. So you can't just analytically integrate that. At least no one's come up with a way to do it yet. Right. But what you can do, you can numerically integrate this, which no one's done, but basically you can do that. So if you numerically integrate that, so here we get, all right, so you can take the derivative, get this equation, and then say the fifth power is bigger than the third power because the coil is expanded versus Gaussian. And then you'll get this expression, which gives you the 3/5 power. So you dump out the 3 term. So it's not exact because you're missing this cube term and some other reasons. So that gives you this 3/5 power. If you actually integrate this, then you get, so it's 3/5 would be 1.67 dimension. If you actually integrate this, you get 1.72. And if you do computer simulations of the self-avoiding chain, you get 1.70. Actually, there's a whole slew of numbers people have gotten and argued about, right? So basically, these are those three, like 5/3. So the 2 is what we get for Gaussian. So this is a log scale. So it's, if you're getting up to 10,000, so it's basically 8 times bigger or something. Chain's like something like 8 times larger between a Gaussian chain and this excluded volume chain. And then these are just showing the 3 options here. Skip the 3 power and get the 5/3. That's this blue line. Actually do an integration, you get this 1.72, which is a red dot, so the black line. And then what people purport is a 1.70, which is green line. So 1.70 gives you 0.588 for this 3/5 thing. So 3/5 would be 0.6, right? And this is 5.88, and this thing gives you 5.80. So people talk about the scaling dimension, which is 1 over the fractal dimension. So nu would be 0.6, 5.88, and 5.8. Right? 5.8, no one's, I mean, that's just numerical integration. That's not published anywhere, but basically it's kind of how that would work. And this thing's been extensively kind of accepted. So you see in papers, the 5.88 number is like a magic number that people will say over and over again. Or they'll say 5/3 for the dimension of it. Right? So anyway, so there's a problem with this. So basically what you're saying is that, I mean, if you have no interactions, no excluded volume, then you have this purple thing. And then if you have excluded volume, so say you're looking at 50,000 unit chain, and you say you'd either have a 2 times 10 to the 2.5 times 10 to the 6 r squared, or you'd have this 10 to the 7 r squared. But there's only those 2 choices, right? You either have excluded volume or you don't, right? So it's a yes or no question. But either the chain avoids itself or it doesn't, right? So that's kind of a problem, because if you look at the race gyration or hydrodynamic radius, so the theta, like a temperature where you're at, the Gaussian is here. So the coil, as you change the temperature, the coil collapses, right? Like a protein folding almost. So basically you're out here, it's good solvent, it's expanded, and it never really reaches a plateau either. So basically you're kind of out here, and then as you cool it down, it gets smaller, and then it reaches this condition, like a theta condition, where you reach a condition where it's Gaussian, and then you can keep cooling, and the coil just has a dramatic collapse. It'll dump down, right? So that's the behavior that's observed. And the theory says like on off, right? So it's definitely not on off. It's got a gradual trend. And also when we did the Boltzmann thing, so we had the second virial coefficient is basically this excluded volume, and it's got a thermal term. So it's like the hardcore potential, and then there's this other enthalpic potential that you have to consider. Right. So, and right now we only have this B. We only have like one term, excluded volume. Right. So how do you get the A term in this is a question. Right. So this is part of the Floyd-Kriegbaum business that was developed in the, I guess, the 50s or something. But so anyway, what they did is they said, like, well, it isn't just a hard core. There's like a Boltzmann enthalpy, like an energy dependence to the thing. this E of R, right? So it's the average energy of interaction for the chain, right? So the average energy, if you make like a lattice of the chain, then you're gonna have like polymer interactions, and say it's in a solvent, a good solvent, and you have solvent interactions and polymer solvent. So if you take polymer and the difference with that, and when it's mixed, and then it's solvent, and the difference in that when it's mixed. So if you swap in a polymer solvent for a polymer solvent, that's the average energy difference of the thing, divided by 2. So basically that would give you like the average energy of interaction for the chains. And then you normalize that by KT. So you have delta E over KT gives you unitless number. Then each, if it's on a grid, then you have Z of those interactions per mer unit. Like in other words, if it's on a Cartesian grid, you have 6, so Z would be 6 interactions of that average energy. In other words, each PP, SS, or SP interaction for 1 mer unit, there's 6 of those. And if it's a Cartesian grid, and there's some number on any other grid. So there's some number Z that's like how many interactions it could have kind of around the 1 unit. Right, so then you define this unitless energy that's an attractive energy, just like the Boltzmann energy. So you have like, this is so you can have phase separation, you have attractive energy between the beads. So they repel each other, hardcore, and there's attraction that's temperature dependent. And you get the excluded volume from that. So this is just that attractive energy. The RT is already included in this chi. So if you want to put that energy into here, then you need to consider, since this is R is for the whole chain, and this is for 1 unit, then you have to consider like how this is going to pan out for the whole chain, right? So to get that for the whole chain, then you say like, well, there's going to be N units in the chain times the units chi. So the energy of interaction per KT per chain is going to be N times the energy of interaction per KT per unit. So that's kind of N times chi. And you say that within that coil of size R cubed, the occupied volume of that thing is going to be N times VC. So you multiply that by the volume, occupied volume, by the energy of interaction per chain. And then you end up with this expression, which can just pop into the Boltzmann. You already took care of KT, so just minus that term. And that term just plops into the chain energy. And this term's of the same form as this excluded volume term that we got like back here. Like this excluded volume term is like N squared VC over 2 R cubed. The thing you get from that analysis is N squared VC over R cubed times chi. Because 2 is missing. Right. So you end up with the 2 would be like 1/2 minus the other thing chi, and you just have the same prefactor. And chi is 1 over T. Right? Chi has this 1 over T dependence. So there's a couple. So this gives you the temperature dependence, and it works. When you do that, you get basically this part of the curve, like this part of the curve up to the theta condition. That part is exactly replicated by this thing. Right? It doesn't say what's happening, but it says like how it could happen. It tells you like how the coil could collapse thermally. In other words, it's not an on-off switch anymore. It's got a temperature dependence. It also tells you that there's a magic temperature. So when, just like here, just like with the Boltzmann, so if you have the Boltzmann and you say, well, this excluded volume term can go to 0 at some magic temperature. So when the temperature would be like B over A, right? Or it's B over RA would give you some magic temperature, like where B2 disappears and then the thing becomes ideal, like ideal gas. So that's a magic temperature, right? Where this critical temperature of something can happen. So you have the same thing with this. You have, this is basically taking the role of the excluded volume, which is like VC is already the excluded volume. Then chi is the A by T term. And if you set those equal, then you find out that when chi equals 1/2, that's where the chain acts ideal. So that means where this term drops out is where you reach that thing, and that's called the theta temperature. That's the magic temperature where this term disappears, and then you get ideal behaviors. That's exactly the point, like where this line is, where the chain like suddenly acts as if it's not self-avoiding anymore. And as you raise the temperature, it becomes more self-avoiding. Drop the temperature and it reaches that point. So this equation can describe up to that line. The rest of it takes something more elaborate. It takes the third viral coefficient to talk about the collapse part. Right? Basically, that's kind of how you can describe this half of it. Right. So what's missing is this doesn't tell you anything about what's going on. Like in other words, it's a thermodynamic equation that predicts the size, but it doesn't tell you how the chain can accommodate that. The chains, so somehow the excluded volume is changing with temperature, but it doesn't tell you like what's really happening. Right. So it took until like the 1990s to figure out kind of structurally what really happens in this case. So we'll talk about that later on, like how that works. But right, so this is a good shot. Like you have a nice prediction of the first part of this curve and the part that couldn't be explained before, right? In terms of this temperature dependence. So anyway, so if you have chi, so the chi is used in this case for polymers in solution. Then it's also used for polymers mixed with polymers using this kind of Hildebrandt mixing term, like the free energy of mixing two polymers together. It's going to be like an entropic part, just like in the Hildebrandt equation for free energy. And then it's going to have an enthalpic term, like a Hildebrandt interaction term. So this actually looks just like the mixing of balls together. This is the entropic term, and this is the enthalpic. Difference is you reduce these numbers by the molecular weight. So because the chains are hooked together, you get less entropy in them. Right? So you just take the volume fraction divided by the molecular weight of each of the units. Then this chi parameter. If you really want to get the Gibbs free energy, you have to add a PV because this is actually the Helmholtz free energy, like the volumetric constant volume free energy. So in order to allow volume change, you need to put in a PV into that. So basically, and Gibbs is kind of what you want for equilibrium. Like you want to have Gibbs free energy change. The chemical potential be like the derivative of that with respect to moles. So you want the chemical potential in the two phases to be equal. So you need this equation with PV to do calculations. But normally people just talk about the first three terms and forget about that. Just call it the Gibbs. Like they just do that. But if you actually have to do a calculation, you need the PV. So anyway, so that thing looks like this. So if you plot that out, if you plot out the this free energy curve, so actually I don't have that plot here, but let me go to this thing. So if you plot that Flory-Huggins equation, they do like delta G over KT equals phi by n 1 phi plus phi by n 1 phi plus phi phi, and like 1, 2, 1, 2 chi. And then there's that PV term too. We're going to ignore that. So if you plot that equation as a function of composition, it depends on what the value of chi is. Okay, so you're going to have and chi equals B over T. This is some number over temperature, like the energy over temperature. Right. So when you're at low temperature, chi's got a big value, and then it dominates this thing. When you get phase separation of that. And if temperature is a high value, chi goes out, and then you get mixing. So you plot delta G over KT against composition, you get this kind of thing. You can think of it as a smiley face. And so basically, so that smiley face means it's miscible. Okay, so say you have something that you make like here, right? And then it's constantly undergoing thermal fluctuations. So the concentration gets large at one side and small at the other side, right? So these fluctuations are happening all the time, like that, about that point where you start. So if it's in the smiley face regime, the up direction is always more than the down direction. You have to have equal fluctuations. So the up part is always larger than the small. That means on average, if you go to this separated state, you've increased the free energy, which is a bad thing. You want to lower the free energy. So that means this is stable no matter where you are. The most stable point would be like right here, where every fluctuation would be upheld from it. Right? So that's the most stable. It's stable everywhere along that smiley curve. Right? So that means the frown curve is where you're going to see the problems. Right? So if you, and this is the temperature is high, or one of the temperatures low, means the chi disappears. So it reaches, this is perfect mixing. Right? And this chi, as you drop the temperature, chi becomes larger. Then you're going to see this business that at some point this thing will go down and just go flat. That's where you're at your magic temperature. TC is like in the van der Waals would be B over A, and for us would be like some other number, right? So it's where the third derivative, the second derivative of delta G d phi equals the first derivative equals 0. Right? So you can solve for that critical temperature. So each of these is a different temperature. This is a lower temperature. Right? And then if you go below that critical temperature, then this thing does a weird thing. It'll have like a divot in it. Might be subtle, but basically it'll have a divot. And these 2 points, so the derivative of delta G dN would be the chemical potential. And this is kind of dN here. So if you draw a line, those 2 points have the same slopes, they have the same chemical potential. So those 2 points are in equilibrium with each other. Right. And then there's also an inflection point here where this thing is like the frown face. Right. That's the sad guy. And then over here, you have the happy face. Oops, his eyeball's messed up there. Right. So it's happy on this side. That means it's missable on that side. It's happy on this side. So even though his eyeballs are messed up. Right. And then it's upset here. It wants to face separate because any fluctuation here is going to go downhill. So it's going to automatically happen. Right. So that's called the spinodal region. So automatically will degrade. If you're in here, it's actually within a smiley face, but it wants the face separate to these 2 points, but it can't because it's already smiley. So small fluctuations will go back to the original composition. If you have a big fluctuation, it'll drive down to that point. Right, so it's called the binodal, that region. And then, so basically in the binodal region, in order to have phase separation, you have to have nucleation growth. And in the spinodal, you have spinodal decomposition. So spinodal decomposition means the stuff, those fluctuations in composition are just going to decorate it. You end up with a web structure that forms. Within the binodal, you're going to get just dots, like spheres. Right, so that's kind of how this gives, how that this is called the Flory-Huggins equation. Right, and that's kind of how it works. So if you take, so you have some temperature here, and temperature TC, and say this is temperature 3 and temperature 1. So then if you plot composition and say temperature, and then you take that TC, which is in the middle, right? And then these 2 points would be like 2 points here. So then if you do others, they'll form other temperatures, you get this kind of shape to it. Where you reach TC right there at 50%. Because it's a symmetric equation. Like you can swap out 1s and 2s, you get the same answer. And then so each temperature here is one of these curves, and you find those 2 points, and you can also find these inflection points for the spinodal, and that'll be like inside of it. So you have the spinodal here, nucleation and growth there. And that's the critical temperatures at the top. So that's called an upper critical solution temperature. At UCSD. So anyway, so that's a normal way like salt and water works. You mix it and you cool it down, it falls out of solution. So you go to colder temperatures, it falls out. Polymers don't work that way, though, usually. Polymers fall out of solution and you heat them up. So if you heat it up, it'll go into and it has a mimicking of that phase diagram. It's called lower critical solution temperature, LCST. Same kind of rules, except chi has a different, it's got a plus A term in it. So it's got, this is an enthalpic. If you get rid of the temperature, it's entropic. So it's like delta H in mixing. That's some kind of delta S that happens when you mix things. So there's this delta S combinatorial entropy, and there's this non-combinatorial entropy that shows up. And that allows you to get this LCSP. So you need to have B making it mix. So these are naturally a negative term because ln of something smaller than 1 is negative. This is automatically negative. This is usually positive and offsets it in UCSP. But if you make B negative, make A positive, then when the temperature gets high, then this term drops out and you only have the positive part, the bad part, and then you get phase separation. Right. So you say this entropy is a bad thing because what you're having is like the chains get together and they organize, and so the system loses entropy when they organize. When you mix the two things together, like say you have a protein and water molecules organized around the outside of it, you've lost a lot of entropy. Entropy is on like how many, right? Entropy depends on how many. It doesn't depend on how much. So if you have tiny water molecules and they all organize around oil, that's a huge impact, even though it might not be that much organized water. Anyway, so that's kind of how this works. So I got some stuff here. So this is PVME. This is like PVME and water. PVME, it's like polyethylene with a ethyl, like an ethoxy group on the side. So if you put a this is a methyl ether. If you put an ethyl ether, so PVEE, I guess, that's post-it glue. No, this stuff is useless. But it mixes. The nice thing about it is it mixes. You can mix this with polystyrene and it mixes. Like it's not any two polymers that mix. And also you can mix it with water and it mixes. So it's water soluble, but it's got an LCST. So if you actually, an LCST is right near room temperature. If you hold this stuff in your hand, it'll go like cloudy, like white. So I got some here. Let's see. You guys can pull it in your hand. So you can get it. I'm not sure which one. This is the most concentrated. I'm not sure which one separates first. Actually, that one should be worse. Anyway, it's also tested body temperature. Or you can do more than one. Some of them will just hold it and then hold it. Body temperature will make it go like. We'll make it phase up. And so it means like if you dump this stuff on the table and you try to wipe it up with hot water, that's a bad plan because it just phase separates and makes goo. Right? It just makes it, and the hotter you make it, the stickier and gooier it gets. So if you want to clean it up, use like ice water. And it's like goes right into solution. So it's pretty weird. So that's like the basic way that polymers behave, you know. So anyway. All right, there's that business. It's kind of a flow through this thing, but that's kind of, since we're talking about, so this is Florey introduced chi parameter here. It's a direct copy of the Hildebrand interaction parameter, except, I mean, slightly different because it's got, basically because he introduces this n term into the free energy equation. So before Florey, so in 1800, there was phi ln phi, phi ln phi, phi phi omega, right? And then after Florey in 1960, there's like phi by n. It's like Nobel Prize, I don't know. It's like not a huge difference. I mean, automatically you're going to get a lower entropy with the higher molecular weight because they're glued together, so they can't move as much. And so anyway, however you want to think about it, this is like one of his also debated that the Russians did it first, like this equation, like a thing he actually got written up for a Nobel Prize, the this rotational isomeric state thing with the bond rotation that we kind of mentioned. So, but that was supposedly this guy Wolkenstein in Russia did it a couple 5 years before and published a book on it in Russian. And supposedly also, like you pick up a Russian polymer science textbook, they don't call this a Fleury-Huggins equation, they call it the some like other guy's equation. Because apparently some Russian invented it earlier. And Fleury was fluent in Russian too, so, yeah, so there you go. So he had all the Russian books lying in his office, and no one's published this in English. Anyway. And there wasn't a lot of communication across the things in the Cold War. Anyway, so that seems to be like a pretty good scenario for this whole thing. So you talk about like if you do a solution, so you just say NB is 1 or NA is 1. In other words, and then you have a molecular weight of the polymer mixed in a solvent. When you do that, instead of being symmetric, this equation like shifts over to the left. So this is the dilute polymer end, and you get higher concentration. The dilute one should have the critical point, actually. So the viscous one should be out here. So it'd be harder to reach that temperature. In other words, this is a UCST, but the normal one would be a LCST, so it'd be this picture upside down. Or if you swap out T for chi, it's a solvent, right? Because chi is 1 over T. So, all right, so that's kind of the picture of this equation for if one of these numbers is 1, one of the NA and B's is 1, it skews it over. So, and you have a critical temperature. So basically, say you want it. So, and then you can write equations for these like take the derivative of that. First derivative is 0. That's a binodal. That's this black line. Second derivative is 0. That's a spinodal. That would be this inside line. Third derivative. Actually, all these are equal at the critical point because all the spinodal and binodal meet. And also, you have the third criteria that the third derivative is 0 at the critical. So basically, you can find the equation for the critical temperature and critical composition are going to be like this, okay? And then if you basically can say that those, if the molecular weight goes to infinity, then both of those are going to be like linear in the 1 over the square root of the molecular weight. So that means that the critical temperature and critical composition for different molecular weights should be proportional to each other. It means on this plot of temperature versus composition, that's a straight line. Like the critical points should follow a straight line going up to where composition is 0, or where molecular weight is infinity. So when you have an infinite molecular weight, it doesn't mix at all. So there's no composition that would be miscible, right? So in fact, the theta temperature is actually the temperature of an infinite molecular weight chain. Right? It's not, so any molecular weight, anything you put into solution like this stuff is going to have a finite molecular weight. It's going to have a phase separation point different than the theta temperature by this gap, right? So that's how it is. So basically in the lower the molecular weight, this thing will shift over to the right and these curves will follow that line basically over. Did you get it?
Yeah.
So the thickest one. Oh, all of you got it?
This one's not the thickest.
Thickest one should be the worst, but according to this plot.
This one we're still trying to get at the bottom.
Okay, I think the thickest one maybe won't work, but anyone get it? It'll turn white.
This one turns a little white at the top.
Okay,
Like you can see the separation.
yeah,
See it, like the cloud at the top.
yeah.
It wasn't like that
It'll
before.
turn like completely white. I don't know. I don't know, it works sometimes. Sometimes it doesn't. Anyway,
You can see the strands too.
yeah, all right. Yeah, it should turn like milk. Like it should be like totally white.
The whole solution.
All the whole time.
Yeah, the whole solution should turn like milk. Maybe I'll bring in a hot plate. You may not have enough human heat here. It's like, anyway, so this thing, so all right, so there's a couple of complications. There's many complications. One is this molecular weight dependence of this whole curve, right? And the other one is that there's a thing called the overlap concentration. So if you take one coil, it's got a molecular weight and it's got a size of R cubed. That means there's a concentration that the coil like carries around with it. Basically, the coil is like a little packet of polymer and it can't be diluted because it's glued together. And there's no way to dilute that thing, right? So there's a fixed, this overlap concentration is a concentration where you start to see the chains entangle. But in this case, it's a concentration where your thermodynamics ends, right? It's an end point to this whole scheme because below that composition, you have a fixed miscibility, like the composition of this equation is fixed below that, because you can't dilute it anymore. Right, so despite that you put in less stuff into the system, then you have like oh yeah, that's perfect. Good, nice. It's because you're wearing a sweatshirt. It's like, yeah. It's a body temperature meter, it's kind of like, take the sweatshirt off. It's too hot in here. But anyway, so yeah, you reach that overlap, like say it's there, and then like after that, all the thermodynamics is fixed at that point, like across there. Right. So say you lower the temperature below that point, even though it should be miscible, it comes out of solution. But it's too dilute. No, you don't make a phase out of that because it's not like entangled. So it's just an isolated coil that can just collapse. You can have a polymer chain that just collapses on its own. Right. So people are using that to make kind of like single molecule nanoparticles. That's what they call it. There's a field of this now. I can find a paper on that. Definitely. Single particle nanoparticles. They can do it by this, and you can also do it by taking the polymer chain and just like super cross-linking it until you get like a clump. Right. So basically this is also kind of what happens in protein folding. Like you're going to have, so it's possible to get this picture where you have the R and you get to the theta point and then you cool down more. So how could you get that? It would just phase separate out. But actually you can get the size of that thing. Right. It's an isolated kind of floating around collapsed polymer coil. It's in the immiscible region, like in this yellow region, right? So if you make a dilute enough solution, cool it down, you can get a collapsed coil at kind of just below whatever that temperature is. So the map of this gets to be pretty complicated. Like you have a good solvent coil kind of in this region. There's a theta coil going along this line, and then there's this phase separation that happens. What did it do? Separate on yours, or is it bottom?
We're slowly getting there.
I think it's like a gradient in temperature. It's got to be. The whole thing should just come. Like,
I'm starting to get like some on the bottom, but it's kind of forming in like a top layer.
it's a temperature gradient issue because it shouldn't do that. It should just be milk, like make milk. That's it, Yeah, that's perfect. That one I like. That agrees with my hypothesis. So I like that. Yeah. It's like paint. All the rest is something's wrong with it. See, there's 4 data points that are totally misled and one that works. So anyway, yeah, so the coil collapse. So we'll look at that coil collapse region too. But what else is in here? A bunch of things on viscosity.
You do this or you do something for it?
I'm a little warm.
Try another one. See if you can probably do all of them as go-to person for the. So yeah, so I guess I'll talk about this coil collapse stuff next time. There's some stuff on rheology and solution here. I don't know if I'll cover that. Maybe I might skip it, but because we'll talk about intrinsic viscosity later on. That's kind of what this is about. So, hey, why don't we quit there for today? I'll try to get. I asked about getting liquid nitrogen, but so. But then when I said like I want it today, like tomorrow, it was last night. I emailed when they didn't come back. It's like there's no phase separate nice. Yeah, it shouldn't do that. Oh, yeah. It should be kind of milky. Maybe a little. Yeah, it should be like that one's good. Oh, is yours separated too?
Once I put it down, it started to.
Oh.
Right.
I was just touching the cool. Oh, yeah. Temperature break. There you go. You proved that it's not.
Yeah.
Wow.
You'll let me know how that water test goes.
Yeah, absolutely. If you get, I mean.